Hello everyone. Today class number 14 for your electrical machine 2. Class number 14 for electrical machine 2. So today I will discuss the phasor diagram of the three-phase induction motor. So what is phasor diagram? Write first definition of phasor diagram. The geometrical relation between different voltages and currents. The geometrical relations between different voltages and currents in a three-phase induction motor where all the EMF equations, where all the KCL or KVL equations, right? Where all the KCL and KVL equations are satisfied. Okay? Where all the KCL KVL equations are satisfied. So, according to the, suppose I would like to first draw the equivalent circuit first. Okay? This is the equivalent circuit. This is Vs, R1, X1, I1 current is entering, I0 current is leaving from here. It will be Re, this is Xm, this is IE, this is Im, and here will be I1 dash, there will be EMF induced E1, here will be EMF induced E2, these are R2, X2 and I2. Okay, these all parameters already I have been discussed in last class. Okay, so from here can you write the equations? So first you have to write the equation. So what will be the equation? KVL or KCL equation for that? So Vs equals to, so apply KVL in primary side, that is the stator part. It is the stator part, this is rotor part. Okay, so KVL at stator. So Vs equals to what? I1 R1 plus J I1 X1. Why J? Because it is a reactive term. Okay, plus E1, right? So make it equation number 1. And then KCL at stator part. What will be the stator part? The KCL will be I1 is the incoming current, which will be equals to I0 plus I1 dash, and again I0 is divided into IE plus IM plus I10. Okay, so as I0 equals to IE plus IM. Okay, so make equation number 2. And KVL at rotor part. So what is KVL? So E2 will be the excitation voltage over here, which will be equals to I2 R2 plus JI2 X2. Okay, so this is your equation number 3. So another concept you have to write, that I2 is induced. I2 is induced due to the current component of I1 dash, that is I2 is phase opposition. I2 is in phase opposition with I1 dash. Okay, I2 is phase opposition of I1 dash. Okay, so let us start drawing. So you have to first complete something. So take, so reference, here we consider the reference axis be phi. Phi means flux. Phi means flux generated. So whatever the flux is emitting through here, so the flux is taken as reference. So I am writing this flux. Suppose phi axis is a reference axis. Okay, first one. And now I would like to express first that the second equation I have to draw it. Okay, first. That is, always remember, this phi is a magnetic component and Im is a magnetic component. So phi and Im are always in same phase. Okay. So write these comments also. Im and phi are always in same phase. And as the IE is an electrical component, Im is a magnetic component, that is IE will be, or Im is a reactive component and IE is the resistive component, right? Im is a magnetic reactive component and IE is the resistive component. That means Im is lags behind the IE by angle 90 degree. So IE will be leading from Im, or Im will be lagging from IE. Okay. So this IE and Im, if we add them, then what happens? IE and Im, if we add, then I naught will be coming. So now let us add them. So how to add? Basic concept: two vectors should be added by making the parallelogram rule. So making a parallel line to that from here. So making the another parallel line from here to perpendicular parallel to it. So we get a resultant. So this is your I naught, right? So I naught, and what is I? So now I naught, before writing the I naught, you have to first set the axis of voltage. So as it is a phi axis, so voltage axis always leading by 90 degree from this phi. So phi axis will be, so we are considering the phi axis first. So your phi axis will be, this is your phi axis, this is your voltage axis. Okay, this is your voltage axis. So from this voltage axis the current is lagging. This I1 dash current is lagging. Why? Because it is a inductive current. There is a RL type load or RL type circuit it is a. So that's why from this voltage line axis the current is always lags behind some voltage phi. Okay, so we are taking the voltage phi. So now suppose I am arbitrarily draw it. Okay, so this angle equals to phi 1. Okay, so now this phi 1 is not lagging from this voltage axis. Okay, so whatever the voltage is due to whatever the voltage is induced over here, that is Vs or E1 you can say. So this type of voltage, always from this type of voltage the I1 dash is lagging by some angle phi 1. Okay, so then you have to again add. So how to add? So I1 dash and I naught, if we add, then second equation will be developed. So okay, so this is your I1. So now this section shows the equation number 2. Okay, this section shows the equation number 2. Okay, so now move into equation number 1. I1 multiplied with R1, I1 multiplied with R1, and then added with J I1 X1. Okay, so what will be I1 R1? So now you have to draw now E1. So now let us consider voltage within this voltage axis. There will be a E1. Okay, suppose we are taking this one as a E1. Okay, that is this EMF. So now this E1 added with I1 R1. So I1 is in phase, this phase. So I1 R1 will be, yes, I1 R1 phase. I1 and R1 parallel to it. So next J I1. J means it will be lagging by 90 degree. Yes, so it will be quadrature of it. So it will be J I1 X1, right? So now if we add from the center, then whatever the line is coming or generated, it will be your Vs. Okay, so this area or this section will satisfy the equation number 1. This section is satisfy the equation number 1. Okay, So now I again move into the third equation. So third equation is nothing but E2 I2 R2 plus J I2 X2. Okay. So now again you have to consider another voltage axis which is exactly opposite to that, because if we consider it is a E1 axis, so it is E1 axis, then E2 axis will be just opposite to it, because we know every action has equal and opposite reaction. So that means if we consider E1 as the action, so E2 will be the reaction of it. So E1 exactly opposite to it, it will be the E2 axis. Okay, it will be E2 axis. So over this E2, somewhere of this axis, the peak of the E2 will be persist. Okay. So now we have to perform this concept, that is the concept was I1 dash and I2 are in phase opposition, right? I1 dash, then I2 is phase opposition of I1 dash. So whatever the I1, just make a opposite. So this is your I2, right? Just opposite of it. I1 dash is in phase opposition of I2, or I2 will be phase opposition of I1. Okay, so this is just opposite of I1 dash. So okay, so this is opposition of I1 dash. Okay, so actually it is opposition of I1 dash, right? So this opposition, so this black color. Okay, so this is your I2. Okay, so now I2 R2 will be, have to draw. So I2 R2 will be, suppose R2 is less than 1. Suppose I am considering R2 is less than 1. If R2 is less than 1, then this I2 will be shorter. Okay, so this will be I2 R2. And if we consider R2 will be greater than 1, then it will be larger than I2. Okay, so now we are taking, for simplicity, R2 is shorter. So we can assume this I2 R2 will be having the less length of I2 phasor. Okay, so next you have to add J I2 X2. So J I2 X2 means, so now you have to put a 90 degree, and you have to draw a 90 degree line from here, so that it can reach a point on this E2 axis. So this amount is actually the E2. Okay, this is your J I2 X2, and this is your I2 R2. Okay, so this is the phasor diagram of three-phase induction motor. So now you have to conclude something over here. So conclude it first. So make this point O, and it is A, it is B, it is C, this is point D. Okay, O. So note, you have to write some notes. OACDO represents equation 2. Okay, it represents equation 2, and OEFGO represents equation 1, and OHI HJ OHI or OIHJO represents equation number 3. Okay, so these three note you have to write, and this is all about of your phasor diagram, which is similar to that of the three-phase in a single-phase transformer, and this is the phasor diagram. Okay, so now you have to write something, the figure caption. So now write the figure caption. Phasor diagram of three-phase induction motor. Phasor diagram of three-phase induction motor at standstill condition. This is standstill condition. Okay, and when there is a rotation, or there is a steady state, sorry, not standstill, it is a three phase at S equals to 0 condition. No, S equals to 1 condition, that is standstill condition. Yes, right, it is a standstill condition. Now if we move the running condition, that is when it is in sleep, it has some particular sleep, then instead of it there will be a resistance, and it is variable resistance. As the sleep is, so it is your R2 dash by S. As the sleep is falling, so it will be cutting, right? It will be cutting. Okay, this is called RL, the equivalent mechanical loading of a three-phase induction motor. Okay, equivalent mechanical loading of a three-phase induction motor, which is not in your syllabus. Okay, no need to write. Okay, so just I am clarify it. It is a for steady state or standstill condition. Okay, so now I will move into the torque equation. So you have to now develop the torque expression. Right. Torque developed by the rotor of an induction motor is directly proportional with number 1, rotor current, that means I2. Number 2, stator flux per pole, that is phi. And number 3, power factor of the rotor. Cos phi 2. Okay, so these three components you have to understand first before writing the torque expression. Okay, so that means the torque is proportional, for first case, torque is proportional to current I2, make it equation number 1. Torque is proportional to flux phi, make it equation number 2, and torque is proportional to cos phi 2, make equation number 3. Okay, so now you have to draw that what is I2. So you have to find the I2 now. So from the KVL equation at secondary, right, from the KVL equation at secondary of a three-phase induction motor, E2 equals to I2R2 plus J I2X2, right? E2R2 plus J I2X2. So I2, take it common, R2 plus Jx2 over here, so equals to E2. So I2 equals to nothing but E2 by R2 plus Jx2. Okay, make it equation number 4. Okay, so now I am finding the I2 now. Okay, so but remember at running condition, so it is, this equation is in steady state condition. So at running condition, the S into E2, sleep will be incorporate with it. Okay, so E2 and X2 are incorporating by a sleep, but there is no component of sleep in case of your resistance. Okay, so here E2 can be written as S into E2 by R2 plus JSX2. Okay, so make it equation number 5. So from equation 4 and 5 you can easily take one, but I prefer the equation 5 because there is a sleep. Okay, in general case you can perform the equation finding the torque expression. Okay, so you have to take the equation 5 instead of equation 4, which is very important to you. Okay, so now here you have to write, so what is cos phi 2? Cos phi 2 means power factor. So from the definition, right, from the definition of power factor, cos phi 2 equals to what? R2 by Z2. R2 by Z2, that means the rotor resistance by rotor impedance, that will be R2 by R2 plus JSX2, right? R2 plus JSX2. Okay, so if we want to find the magnitude only, so that will be equals to root over of R2 square plus A square X2 square, right? R2 square plus r2 square by r2 square plus a square x2 square. Okay, so this is your cost. We make it equation number 6. Okay, so now from equation 1, 2, 3 and 5 and 6 we have t is proportional to e2 by, from equation 5 es e2 by r2 plus, okay, so make it root over square. Okay, make it root over square. Okay, so root over of r2 square plus a square x2 square. Okay, so multiplied by 5 and multiplied by 5 and then r2 by root over of r2 square plus a square x2 square. Okay, so t is proportional to s e2 r2, and now if we put this phi, so phi can be written as k into e2, that is phi equals to k into e2 because phi is proportional to e2. Okay, so divided by root over of r2 square plus, so after multiplying these two, so it will be looks like r2 square plus a square plus x2 square. Okay, so your ultimate torque expression is k s e2 square r2 by r2 square plus a square plus x2 square. Okay, this is your torque expression for 3-phase induction motor, general torque expression, right? This is the general torque expression for 3-phase induction motor. Now there is a lots of torques are there. So the classification of torques I will discuss in next class. Classification of torque will be discussed in next class. Okay, so wait for the next class. I will come back. So today's class up to this much. Thank you.